So we're on, if you're following along on the learning objectives, we're on the last section, Unit 7. Again, this doesn't have a whole lot to do with atoms and molecules and electrons and all that stuff. It's sort of, I would say, on the periphery of what I would call core chemistry. Okay? We're going to start talking about reaction rates and equilibrium. We briefly talked about equilibrium. We haven't talked about rate. Hopefully my batteries haven't reached equilibrium. Laser pointer work.
Or plasticate.
Yeah.
True.
Too great.
Sorry, homework.
Okay. Reactions can happen fast. Reactions can happen slow. Looking at some of the reactions we talked about, and reactions that you know, what happens if you mix vinegar and baking soda? It happens really fast, right? But some of the reactions we talked about are like silver jewelry tarnishing or copper penny tarnishing. That happens really slow, right? So there we have two reactions. One happens very fast, one happens really slow. Up here are two pictures of very similar reactions. They don't look similar at all. What is similar about them? Oxidizing, exactly. Here we have a match burning, it's reacting with oxygen, it's oxidizing. This is iron turning to rust. It's rusting, it's reacting with oxygen in the air, it's oxidizing. But what can you say about the speed of these two oxidation reactions?
The match is faster, the chain is slower.
Right. The match is very fast. The chain rusting is very slow. So we have to figure out what determines how fast a reaction goes. Why is this one fast and that one slow? There are several things that determine how fast a reaction goes. The most obvious one is temperature. Okay? You probably realize if you heat something up, it's going to react faster. Also, if you use higher concentrations of your reactants, they're going to react faster. If you put baking soda in vinegar, and then you put baking soda in vinegar that you've diluted 10 times, you can imagine the one in more concentrated vinegar is going to a whole lot faster, right? You can also change the surface area. Just like when we were dissolving our sugar, if you put a sugar cube in the water, it dissolves slower than if you put in granulated sugar. Same thing happens here. If you have a solid that has a lot of surface area, it's going to react a whole lot faster than the same solid that's in a cube form or something where a lot of the material is sort of hidden in the center of it. And we can also add a catalyst. This one, you've certainly heard of catalysts. You may not know what a catalyst is. You may not be able to picture in your mind what a catalyst does, whereas these are a little more easier to imagine. So, here again, we have two flasks with a balloon on top. The balloon allows us to see the formation of a gas. The gas is going to be our product, so if the balloon fills up faster, we know that the reaction is happening faster. If you were looking at these two flasks, before and after reaction, which one would you say had the higher concentration of reactant in the liquid? Why? For those of you out looking on the video on the camera, he went. Yeah. So we form gas a whole lot faster on the right than on the left. Okay? That means the reaction happened faster, which means that this liquid had to have been a higher concentration. This is how surface area affects it. What we have here is a jar with an iron nail hooked up to electricity, and then my guess is there's probably condensed oxygen in the bottom. Over here is the same bottle with the same oxygen with steel wool. They're both steel. The only difference is this one has a whole lot less surface area than that one. Turn on the electricity and look what happens. This one more or less just glows orange because it's hot, but it's not really reacting very fast. Whereas this one is reacting so fast that there's sparks flying everywhere. Okay? The steel is reacting with the oxygen. It's basically rusting, but this one is rusting a whole lot faster. Because almost all of the steel here is exposed to the oxygen. Whereas here, the only part of the steel that can react is the stuff that's on the outside. If you're a steel molecule buried in the middle of that nail, you're never going to see oxygen. You can't react no matter how bad you want to. This is a piece of liver. Okay? I don't know from what species. If you put hydrogen peroxide on liver, it bubbles. Okay? If you put hydrogen peroxide on this table, it's not going to bubble. There's an enzyme in liver called catalase that breaks down hydrogen peroxide. Okay? An enzyme is a protein that serves as a catalyst. Everything in our body that does anything is caused by enzymes. Okay? If you've taken biochemistry or probably anatomy and physiology, you know all about enzymes. Enzymes make life go. But all they are catalysts. Okay? A catalyst makes the reaction happen faster. Everything in our body that happens would happen in a completely universe void of life. It would just happen so slow that nothing like an animal or a plant or an organism could exist. The enzymes make everything happen so fast, which allows us to exist.
Is that why, like, with hydrogen peroxide, you know how we put it on scars and stuff? Is that the same enzyme, or is that just only in liver, that particular enzyme?
I've never put hydrogen peroxide on a scar. Does it bubble when you do it?
Mhm.
It does.
And it's usually the reaction with, like, I don't know if it's because of the bacteria that's in it that makes it bubble like that, but it's supposed to help clean out
Yeah.
scars.
So hydrogen peroxide will oxidize whatever it touches.
Okay.
So if you put it
So
on,
it could be a different catalyst, basically, right?
it could be. It's probably catalyzed. Liver probably just has a whole lot more of it per unit of liver.
Okay.
It's a matter of if hydrogen peroxide oxidizes anything it touches. If you are a single cell bacterium and you get oxidized, you're toast. Right? Nothing you can do about it. If you're a person, you can sacrifice a few cells, skin cells, in that cut, right? If you oxidize a few of your own cells and kill them, so what? Wait a day and they'll grow back. Okay? So if you put it in there, you're kind of sacrificing the tissue around it to kill all the bacteria that are in there. To understand why these things affect the rate of a reaction, we have to sort of think about what this reaction looks like on the molecular level. And we do that through something called collision theory, which simply put means for two molecules to react, they have to hit each other. Okay? Makes sense. Remember, the molecules are flying around randomly, and every once in a while, they hit each other and bounce off. But if they're two things that want to react with each other, when they hit, they react, and then go their separate ways. When they collide, two things have to be right for them to react. One, they have to hit in the right orientation. And two, they have to hit hard enough that they react. Imagine two molecules. Here's one, and here's one. Okay? If this end of the clicker wants to react with this end of the stapler, if they hit like this, no matter how hard they hit, they're not going to react. But if they hit like this, now they can react. Okay? And also, if they hit like this, but they hit really slowly, they don't have enough energy to react, they still hit and bounce off. So they have to hit like this, hard enough to react. We talked about energy diagrams. And you didn't really know what you were drawing. You kind of drew a line. You knew, yes, was it higher at the end than it was at the beginning, or was it lower at the end than it was at the beginning? But there was always this little bump there. And we never talked about why. So is this an endothermic or an exothermic reaction?
So, I think it's endo.
It's endo. Why? Why is it endo?
Isn't it because it's the higher the energy, like as it's going?
Right. An endothermic reaction absorbs energy. Here's reactants, here's products. Products are higher than the reactants. They absorb energy. Here, an exothermic reaction, products are lower than the reactants. It's exothermic because it released energy. Both of them have this little bump. Okay? Imagine this just like a roller coaster. To get from here to here, you have to ride this line. You can't go straight from here to here. You have to follow that line. So in both cases, you have to go up to come back down. Which means, in both cases, both an endothermic and exothermic, at first, you have to absorb heat or energy. It doesn't matter where you're ending up. Starting out, you have to absorb energy. Okay? Think of this as me sitting in this chair. And all of a sudden, Holden reaches into his bag and he pulls out an ice cream sandwich. Okay? I would be much happier over there with the ice cream. But I'm over here. So I have to get up enough energy to get over there to get to the ice cream. So I have to decide, is it worth it? And do I have enough energy to get up and walk all the way over there? Okay? So that's basically how the reaction works. There's a barrier. I have to say, okay, I want to do this. I have enough energy to get over there. Okay? Same thing happens in a reaction. Here's our reactants. This is ozone. O3 is going to react with nitrous oxide, or nitrogen monoxide. Okay? In the end, we're going to have oxygen and nitrogen dioxide. But to begin with, it has to go up here, or it can come down here. At this peak, we call it the transition state. You may see somewhere, possibly in your book, called the activated complex. We're going to call it the transition state. Okay? The transition state is sort of halfway between this and this. Molecules don't like to exist in this state, which is why you have to put a whole bunch of energy in to get this to exist. But once you're at the top of the mountain, you can fall down the other side. Okay? So think of it just like a roller coaster. You come out of the station, you hook up to the little chain thingy, and it has to pull you up. If gravity wants to pull you down, you're going to have to do some work. The chain's going to have to pull you up in order to let gravity pull you down the other side. Okay? If we add a catalyst, what happens is it lowers the height of this transition state peak. Instead of having one big peak, we now have two small peaks. It's a whole lot easier to get over, which means its activation energy is lower, the reaction's going to happen faster. Okay? Activation energy is the energy between the reactants and the transition state. So it's this line here. That's the activation energy. A molecule has to have that much energy to get to the top of that hill to fall down the other side. If you don't have enough energy to get to the top of that hill, no matter how much those molecules want to react, they can't do it. Probably the biggest place you've at least heard of a catalyst is in the muffler of your car. No, it's not. Yeah, it's just catalyst and muffler, isn't it? There's
No,
also the
separates.
catalytic converter,
Yeah.
which is further up. It's up front, right?
That's closer to the owner.
So what this is, the catalytic converter in your car is a mix of palladium and platinum. So there's palladium, there's platinum. You know platinum is expensive. Palladium is also very expensive. But the great thing about catalysts is they don't get used up. They're recyclable. You can use them over and over and over again. So you can put just a very, very thin lining of platinum and palladium in that catalytic converter, and it'll last for years and years and years. Okay? What happens is when you burn your gas in your engine, you make carbon monoxide. If we just put a whole bunch of carbon monoxide into the atmosphere, that wouldn't be a good thing. Yes, we now know that putting a whole bunch of CO2 into the atmosphere isn't a great thing either, but at least CO2 isn't toxic to us by itself. Okay? Carbon monoxide will kill you very fast. Same thing with nitrogen monoxide. We can convert nitrogen monoxide to nitrogen gas and oxygen gas, which are two good or neutral things. We don't really care about if we make any of those. So what happens is we have our catalytic converter, carbon monoxide comes and sticks to it, an oxygen molecule sticks to it, next to it, kind of holds them in place, and holds them in place right next to each other, giving them time to react. If they're bouncing around, when they hit, they have to react right then. Otherwise, if they don't react right then, now they're not next to each other. If they come and sit next to each other on a catalyst, they're sitting, they're sitting, they're sitting, they have all the time in the world to react. So here is an example of drawing an energy diagram. This is a reaction. The question says, draw the energy diagram that shows the relative energies of the reactants, products, and transition state. And we also want to have to label a whole bunch of things on here. Does anybody want to come up and try to draw this? No? So, we have axes. Hopefully you can get that far. Reactants always start in the same place. I'm just going to draw a line here. What happens after reactants? Where does the line always go after the reactants? Up. So I can take this up to the top of the hill. Now I have to figure out where I'm ending. Where am I going to end? Down from here. I have to go down. How far down? Why slightly? Because it's endothermic. Up here it says it's an endothermic reaction. It wasn't clear, it wasn't jumping right out at you in a bullet point, but it does say it's an endothermic reaction, which means our products are going to have more energy than our reactants. So wherever we draw our line for our products over here, it has to be higher than this. But it also has to be lower than that, right? That is always the top. So I'm going to draw it like that. Okay? Now we have to label some things. Where's the reactants? On the left. Those are reactants. Where are the products?
Right.
On the right. It doesn't say it, but where's the transition state? In this case, it also wants us to draw a possible structure. For here, it says activated complex. That's what we're going to call the transition state. So this is our reaction. So our reactant is NO2. So we'll say it looks like this. Okay. You'd have to do the whole Lewis dot structure thing to figure out what it's going to look like. Okay. We're going to say NO2 looks like that. Our product, we have NO and O2. What might this transition state look like? Compare the reactants to the product. How many nitrogens do we have over here? One. How many do we have over here?
One.
One. How many oxygens do we have over here?
Two.
How many do we have over here? Three. We can't make an oxygen. It has to come from somewhere, which means this doesn't just break apart.
Does it form? Like do two form?
Right.
One?
Which actually, if we look up here, it tells us that. Two NO2s break into that. So we have to look at this and figure out how can we stick two of those together so that it kind of looks like these two things. In this case, there is no one right answer. Either it's possible or it's not possible. Okay? We can't know what a transition state looks like. They're so unstable, once you get to the top of that hill, they fall off the other side. So they exist for such a short period of time that we can't tell what they actually look like. So no one can prove you wrong unless you say it looks like chemistry cat. Then it's clearly not right. Okay?
The only thing I could really compare it to, because there's two separate ones on the product side, wouldn't there mean, there obviously has to be a second one formed in this transition phase, right?
Right. So let's try this.
Well, that
It
makes
says
more
there's
sense.
two of them, right?
Then you just
And
form.
then over here, we also need two of these.
Well, that makes a little bit more sense. Then you would just combine those other two if they're the two on the left, you would just fuse the middle ones into one, don't you
Right.
think?
So if I go like this, there's my two that like that, right?
And then those two in the middle would be together, right?
If those combine together to get that,
Then
I
those
then
separate.
have that and that.
Yeah, that makes sense.
So it's all just kind of spatial of looking at it. You would not have to predict what a transition state looks like. Okay. But I want you to see how this process works. Okay. To get from here to here, you have to go through something that's kind of a mixture of both of them. Okay. So if you were really drawing this, what you could do is you could, and it's possible the next slide shows this, these bonds that are breaking and the bonds that are forming would be dotted lines. Okay. These two are breaking, that one is forming. These two don't change at all. So they don't show those bonds, but there we have our two NO2s next to each other. The oxygens in the center are going to break off and form their own O2.
Why'd you say something funny looking T extra line? Is that just to symbolize the transition?
Yeah, don't worry too much about that. What that means is it's saying that it's called a double dagger, and that traditionally means activated complex or transition state. And it's just saying everything in there is sort of, it's a mess. We don't know exactly what it looks like, but here's kind of what it looks like. This impacts equilibrium. Okay. Say you got the top of the roller coaster and the roller coaster broke. And you're right at the top and a gust of wind comes. What's to say you're going to fall that way? You could fall backwards, right?
It depends on where the wind blows.
Right, it depends on where the wind blows. A roller coaster isn't a one-way track unless there's safety features built in, which hopefully there are. But say you're on the very first roller coaster ever made, okay? There are no safety features. You're at the top, you stall. You could go backwards, you could go forward. A chemical reaction is the same way. If you're up here, you can go back to the reactants, or you can fall over to the products. And if you're the products, if you get enough energy, you can go backwards up to the transition state and back down to the reactants. Okay? Up to this point, all of our reactions have been one-way streets. But in reality, basically every reaction is a two-way street. The reactants are constantly becoming products, and the products are constantly going backwards to make reactants. But usually, this reaction happens so much faster than the reverse one that to us, it looks like a one-way street. What happens when you have these reverse reactions happening is you get an equilibrium. We briefly talked about equilibriums, or equilibria, and it's kind of a in-between. It's a state where two things are happening, but when you look at it, it looks like nothing is changing. Right? It's like when we put our cup of water on the table and we put a box over it. The water evaporates until you hit the vapor pressure of the water, and then the water keeps coming out of the glass into the gas, but the gaseous water also goes back down into the glass at the same rate. So to us, the level in the glass stops changing. We're at equilibrium. The water molecules are leaving the glass at the same rate they're going back into it. This is an equilibrium of a reaction. This is just sort of a rearrangement or a decomposition reaction. You have N2O4, it becomes 2NO2. So it just breaks apart. So reactions that can happen. N2O4 can become NO2, two of these NO2s can actually come back together and form an N2O4. So here's a jar that we put N2O4 into. At the beginning, we have almost all N2O4, and then that looks like a NO2. Okay? Over time, the N2O4 breaks apart, and we get more and more of these NO2s and fewer and fewer N2O4s. Eventually, we get to a point that it stops changing. So, did it change from here to here? Did it change from here to here?
Mhm.
Did it change from here to here?
No.
No. At this point, we hit equilibrium. At this point, the N2O4 is breaking apart at the same rate as it's forming. So individual molecules are still reacting. But to us looking at it, the reaction is stopped. We're at equilibrium. We can explain this mathematically, okay? This is going to look, at first glance, pretty complicated. It is not, okay? So don't make it complicated, okay? This is a reaction. A and B are our reactants. C and D are our products. The lowercase a, b, c, and d are just the coefficients in front of them. When we write something called the equilibrium constant expression, we put the products over the reactants. Products over the reactants. Remember that. Say that in your head a million times. Products over the reactants. Okay? Always. Products over the reactants. These little brackets mean concentration. If I have brackets around C, that means the concentration of C. Generally, that's going to be in molarity. So here, we have the concentration of C in molarity raised to the power of the coefficient that was on C in the equation. You multiply that by the same thing for the other product. The concentration of D raised to the power of the coefficient that was on D. We do the same exact thing for the reactants on the bottom. A to the power of A, B to the power of B. If you put the concentration of each thing in here, you're going to get a value. And if you take the concentrations at equilibrium, you will always get the same value of K. So that K is called the equilibrium constant. There are two types of problems you can do here. If you're given KEQ in 3 concentrations, you can solve for the 4th. You can also be given 4 concentrations and have to solve for K. Okay? So here's an example. Here's a reaction. Nitrogen gas reacts with hydrogen gas to give us ammonia gas. First part of the question is, what is the equilibrium constant expression? So it's what over what? Just in general, what's the rule? It's always the what over the what?
Products or reactants.
Products over reactants. So in this question, what's our products?
Ammonia.
Ammonia. What's our reactants?
Nitrogen, hydrogen.
Nitrogen and hydrogen. So the very first thing I'm going to do, products over reactants. Now I have that, I can go back and put the exponents in. What's the exponent on my ammonia? 2. It's just the coefficient off of it. take that 2, I put it there. What's my exponent on my nitrogen? 1. So an exponent of 1 doesn't change anything, so I just leave it off. What's the exponent on hydrogen?
3.
3. I say equals KEQ, and I'm done with the first part. That's it. Now the second part says, what is the value of the equilibrium constant? Normally on an exam or a quiz, you would just be given the values. Straight out, concentration of this is this, concentration of this is this. On this slide, they're making you think a little bit harder. Some graphs here. You have to pull that information off of the graphs. First of all, which graph are we going to use? The one on the left, the one on the right?
On the right,
Why the one on the right?
but there's no value for
Right, so
NH3 and left.
you're thinking mathematically. If there's no value, if there's 0, this isn't going to work. Right? Conceptually, why would we use this one instead of that one?
Equilibrium concentrations.
It says equilibrium concentrations. We're dealing with equilibrium, not initial concentrations. We're at equilibrium. So we want these. So all I have to do is plug those numbers into here. Once I plug them in, I can treat these brackets like parentheses and do the math. So what is the concentration of ammonia?
0.280.
So I'm going to go 0.280 squared over, what's the concentration of nitrogen?
0.0600.
0.0600 to the power of 1. Concentration of hydrogen,
0.180.
80 cubed. If you do the math, you'll get a number.
It'll end up being like 2.4, is what it says on the next page.
Is that what everybody gets? When you do this, make sure you put it in your calculator correctly.
Because it's sig figs, right?
Yeah. So there are how many sig figs? 3. Like I said, if you put this in your calculator wrong, it's going to do everything in the wrong order. It's not going to give you the right number. So make sure you're comfortable putting something like this in your calculator. What is the number?
224.
2.24?
No, 224.0512117.
Is that everybody got 224 or something?
Yeah.
So 224. If there are no units. A K value has no units. It's just 224. So if you put, in this case, if you put units, you're going to get the little rat stamp saying check your units. Okay? In this case, you have permission to not put units. And that is the end of it. So if someone who's not here at the moment walked in that back door and saw that, they would get really scared, right? That looks scary.
That and like the exponents and all the letters.
Brackets and division
The
and
double add
K's
calculus
and
math.
variables and all kinds of stuff. It looks scary. Is it hard?
No, but all we have to make sure is we want to do is for equilibrium
Right.
and not the initial concentration.
Right.
Because there's
You won't have a problem like this, okay? A slightly more difficult version of this problem would be, here is the value of K. Here are concentrations at a given point in time of your 3 things. Is this reaction at equilibrium? And the way you would do that is you plug the numbers in.
Solve it, see if it equals that.
If it equals that, it's at equilibrium. If it doesn't, it's not.
Hopefully that's correct.
Yes, hopefully your math is
Never
correct.
have to calculator.
We talk about reactions as reactant favored or product favored. That means when you get to the top of that hill, does it want to fall backwards to the reactants, or does it want to fall forwards to the products? We look at this, this is a fraction, right? These are products, these are reactants. If something is product favored, that means it wants to make product. At equilibrium, you're going to have more product than reactant. If you have a fraction, and you have more product, so let's see. Does this look scary? Oh, we had just said if someone walked in the back door and looked at that, it would look very scary. But when you talk to somebody and you see the video, it's not scary. Okay. So if we have a fraction and we have a whole bunch more on top in our products, we do the division. What can we say about the value of k?
You know, a whole number?
It'd be greater than 1.
Greater than 1.
Yeah, that's what I meant.
Yeah. So it's greater than 1. In a fraction, if the top is larger than the bottom, it equals more than 1. If something is reactant favored, it does not want to make much product, you're going to have more on the bottom. In that case, what can you say about k? It's less than 1, right? Think about it in terms of a fraction. A half. 1 divided by 2 is 0.5. You know that. So k is less than 1. If you have 2 and 1, it's 2. 2 is more than 1. What if it favors them equally? You get stuck right in the middle. What can you say about k? If the top and the bottom are the same, what is k? 1. Exactly 1. So we have 3 different possibilities. If they're equal, k is 1. If it favors the products, k is more than 1. If it favors reactants, it's less than 1. So in this example, is this reaction reactant or product favored?
Product.
Correct. Product.
Product. 224 is more than 1. We had a whole lot more on the top than we did the bottom. Top is product. So this reaction is product favored.
You just tell that by looking at the graph here, or do you have to do math because the numbers, because you know the product numbers,
You have to do the math. Because
that's the exponent.
these two are going to combine together. And in order to do it, by looking at it, you would have to do the math in your head.
Right, yeah, I forgot the exponent.
So that's exactly what we just said. K more than 1, K less than 1, K equals 1. Here's another example. We have a reaction. So we're given the concentrations at equilibrium. This is more like you would normally see. It's just flat out given to you, not in graph form. We have to do some things. Does anybody want to come up and do it? No.
I mean,
You're doing an excellent job.
That's why they pay me the big bucks.
It's just the first one? It's just the first one, like write the constant expression?
Well, if you want to just do the first one, then you're welcome to just do the first one. You're welcome to do all 3 if you want.
I'm not confident to do all three, but I think.
If
I
you're
can do
comfortable
it.
doing one,
First
do
one?
one.
I think I can do the first one. I'll try. So, do I have to, do you want me to do the letters first, or can I just plug in the numbers if I'm doing the first one? Right?
If it asks for equilibrium constant expression,
They
what
want
it's
just the
asking
letters,
for
right?
is the letters.
Okay.
The letters with the numbers for the exponents.
Okay. Okay.
Yeah, then you have to put equals KEQ.
Oh, that's right.
Don't forget the equals KEQ, that's part of it. That's it. Done. Yeah.
You only have one compound like in this reaction, and it goes both ways.
Mhm.
Does it matter which one's a product and which one's a reaction?
Yes. If you flip this, and you put, say you have these numbers, and you plug them in. If you flip that fraction, you're gonna get a different number.
I was gonna say,
Right.
was that right, product over reactant, right?
Product over reactant.
Okay.
So I would just always follow the order left to right that they use.
Correct. You could rewrite that the other way, but you're going to have a different KEQ equation. Okay?
Would the value be the same or no? Shouldn't it be the same if you're just going backwards?
Think of it this way, if you have a product favored reaction, your K is going to be more than 1. If you flip this reaction backwards, now it's the same reaction, you just wrote it backwards. Now it's going to be a reactant favored reaction, which means your KEQ is going to be less than 1. So it's just everything is flipped upside down. So who wants to do part 2?
Isn't that just plugging, it's just plugging in
It's
those
just-
top numbers. The Celsius, the 25 degrees Celsius is what threw me off. This is that equilibrium, you just plug it in, right?
It says we're at equilibrium and we are at 25C.
So, and you're just, okay.
That 25C is there to throw you off.
That's why I wasn't confident in it, but that's easy.
But what if it was like?
If you were at a different,
Yeah.
if you were at a different temperature, you couldn't do this. You can't do it.
The fact that it rewrote it down there.
Because
That's what,
you don't have any way of predicting how that temperature is going to affect things. You just
Well,
can't.
then I probably could have done that.
You want to do it?
I mean, I might need help with the math ahead of time, but like trying to do whatever 0.0750 squared is. I mean, I know how to write it, I just wouldn't. Does anyone know what that is squared, the 0.0750 squared?
0.0056.
And then I don't know what the math of that would be.
222, and then just repeating 2 forever.
Should I put the K, E,
Yes.
Q in front here this way?
At some place, you have to say KEQ equals that.
Okay, so if I did it like that and then equaled it all the way
Yes,
out?
because equal, which means that equals that.
I hope that helps.
So you could also write equals KEQ at the end, because everything's equal, it doesn't matter what order you put them in, mathematically, they're all equal. So then part 3, what can you say about the position of equilibrium? Product favored. We're a whole lot larger than 1 product favored. That's it.
Sweet.
That's these problems. Products over reactants, take the coefficients, make them exponents, plug in your numbers. Done. Okay? My guess is more people are going to get this question wrong because they put it in their calculator wrong than are going to get it wrong because they set it up wrong. You will. Well, on the final you
I'm
will.
trying to remind myself how to use this.
on multiple choice, you don't get it. You don't get partial credit. Okay. I think the last concept for today is what happens when you disturb the equilibrium. And this is Le Chatelier's principle, or Le Chandelier's principle if you're American. Okay? What happens if we're at equilibrium and we add something to it? Okay? Think about it. It's a weekend. You're in your happy place. You're at equilibrium in your lazy boy. And all of a sudden you realize, crap.
I've got chemistry going.
Yeah. You're no longer at equilibrium. Something has to change. You have to do something so that you can get back to equilibrium. Okay? If we're at equilibrium and we add one of the reactants or one of the products, or if we remove a reactant or a product, equilibrium gets disturbed. And it's going to shift to get back to it. Le Chatelier figured out what happens if you do each of these things. And in this case, in this situation, you're not going to do the math to figure it out. You're just going to conceptually, what happens to the equilibrium? How does it, which direction does it shift to get back to equilibrium? You can take a reactant out. You can take a product out. You can change the temperature. You can add a reactant. You can add product. If you're dealing with a reaction that's in that's gas phase, if you change the volume of the reaction container, you're going to change equilibrium. If you add a reactant, the reaction shifts away from it. If you take something out, the reaction shifts towards it. Think of it as if you have this reaction. A and B come together to make C and D. If I reach in and grab some of this A, pull it out, it kind of creates an empty void here. And everything falls back to the left to fill that void. Okay? If I add extra D, I create a little extra over on this side, so that falls over to the left. Okay? If you add extra of something, that extra wants to go away. So the reaction is going to go to the other side. If you take something out, the reaction is going to want to replace it. So it's going to go towards it. So if I add a reactant, if I add some of this, it wants to get rid of it by going over here. If I add a product, if I add one of these, it's going to shift. To get rid of it, it's going to shift to the left. If I take some of this out, some of this is going to come over here to replace it. If I take some of this out, this is going to shift over here to replace it. Okay. Here's a reaction where we have yellow molecules, we have green molecules, they're at equilibrium. If we're able to take an eyedropper, go in there and take out some of the yellow molecules, all of a sudden we're not at equilibrium anymore. We have our equation, we're at equilibrium. If all of a sudden I change this number, now all of a sudden this fraction does not equal 222 anymore. So if I take some of this out, some of this has to come out of here and go back down here to make it so our fraction equals 222 again. So in our picture, we take out yellow molecules, some of our green are going to turn yellow to replace them. Companies that are making things, or if you're in a lab and you're making something, you can use this to your advantage to get as much product out as possible. There are two ways you can do it. One of them we talked about in lab last week, using excess reactant. If you run this reaction and it gets to equilibrium, you're stuck in the middle. So you still have some reactants left. You haven't made all the product that you can. But if you then add a whole bunch extra of A, you shift your reaction way over here to make as much product as possible. Also, if you have a way of taking out that product as you make it, you're never going to reach equilibrium, so these will keep reacting to replace the product that you take out. So here's an example of a type of problem you would use this for. Here's our equilibrium. We're going to do some different things to it. We just have to say whether the reaction is going to shift left, right, or not shift at all. So here's our reaction. If we remove silver ion, okay, I should delete that for next time. Ignore the whole NaOH thing. Okay, that's an explanation of how you're doing it, but NaOH isn't anywhere up there, anywhere else, so that's just confusing. Okay, just focus on silver ion is removed. If you remove silver ion,
Will it shift to the right?
it shifts to the right. If you remove something on the right, it wants to replace it by shifting to the right. If we add silver nitrate, and it's tells us silver nitrate is soluble in water, which way is this going to shift? Now silver nitrate is not up there, right? So you're going to have to think about this one. What happens if I add silver nitrate, and assuming this says it's happening in water?
It wouldn't shift because you're adding it to both sides, right?
But it's
Because
happening.
if you're adding silver nitrate, obviously as a reactant, then wouldn't it be a product too? So that you're adding to both sides, which is not shifting, right?
You don't necessarily add it to both sides. You add it to the beaker or whatever, and then it happens to be on the left or it happens to be on the right if you write it out. Okay? So, is silver nitrate on the left or the right?
So we're technically on the right because it'll be a product, right?
On the left,
Oh, it's on the left.
is this a reactant?
What happens if you add silver nitrate to water?
You do, yeah, silver ion.
You get silver ion and nitrate ion. So by adding silver nitrate, you're adding silver ions. Not directly, but indirectly. It's not silver ion when you add it, but as soon as you put it in that water, it breaks apart, and now we have silver ion. So if we add silver nitrate, does the system shift left, right, or not change? It shifts left. We added product, we now have extra product, it's going to shift to the left.
So it was an added product, not an added reactant, correct?
Correct.
Okay.
Here we have silver iodide, it's a solid. Adding silver nitrate does not affect how much silver iodide we have. Hmm?
How do you know which side you added it to?
We had
Not one.
We have silver nitrate. If we dissolve it in the water, it makes silver ion plus nitrate ion. The nitrate ion is completely irrelevant to us.
Oh, so we're not caring about the equation underneath the top anymore.
Well, we do. We do. So we added silver nitrate. It became silver and nitrate. Like I said, nitrate is irrelevant to us. Nitrate is nowhere up there. But we added silver ion to our reaction. On what side is silver? It's a silver ion.
On the right.
It's on the right. So we added product.
So there's two separate reactions going on in there, and then at the end,
Yes, there's two reactions. The silver iodide,
that's why I was confused about that.
silver iodide
Okay.
is becoming those two things, and those two things are becoming silver iodide. But the reaction is written in this direction. So these are the reactants in this situation. These are reactants. These are products. So if we add silver ion, so on the right, it's a product, which means it shifts to the left. Would this problem be easier? Would it be less confusing if it just said silver ion is added to the system?
I don't think it makes much difference. I mean, I don't know.
To me, I think, yeah. Just because you would automatically see the AG.
Silver ion.
You see, it's right there,
Right.
right? It's that extra step.
Yeah.
You have to see, silver nitrate is going to break in, is going to give me that. So by adding silver nitrate, I'm indirectly adding a product. So it's going to shift to the left. What happens if I add sodium iodide to the system?
Just to the right.
I heard left and right.
Right.
If I add sodium iodide, what does it form? Sodium and iodide. Did I add a product or a reactant? I added a product again. Right?
Shift to the left.
It's going to shift to the left. What happens if I reach in and I pull out some of my silver iodide? Shift left or right? Shift to left. If I pull this out, it's going to fall back to the left to replace it. If I somehow remove silver ion, is it going to shift to the left or to the right? To the right. If I remove a product, it shifts to the right to replace it. If I'm at equilibrium and I add more silver iodide, does it shift to the left or the right? To the right. I now have too much reactant. It's going to shift to the right to get rid of it. Okay? That's the end of that chapter. Right. Do you want to take a break or do you just want to move on? Okay. So we got 1, 2, 3, 4, 5, 7, 8, 9, 10, 11, 12, 13, 14. We have 15. Do you feel like you can, without hurting anybody's feelings, break into 3 groups of 5?
Yeah.
Okay. So if you break into groups of 5, if you have your homework in your group, just kind of go over the homework. Find somebody in your group that knew what they were doing on the problem you didn't. And then if nobody does, raise your hand and I'll come help sort it out.
I'll move. Yeah. I mean, we worked on it last week. Unless you change that.